Hello and welcome to AP Chemistry Big Idea 4 Chemical Kinetics Notes. I'm Mr. Coro, and today we're going to tackle mechanisms. So mechanisms have 5 major parts to them, and we have to go over each individually. Today we're going to talk about potential energy diagrams and how collision theory affects them, and rate determining steps of specific reactions and all the steps that go along with them, which are known as elementary steps, how all those elementaries set up to net equations, and we have to identify within those elementary steps intermediates and catalysts. And last but not least, talking about rate law determinations of mechanisms. Okay, let's get started. First thing on our list is potential energy diagrams. Potential energy diagrams show how energy changes from when you start as a reactant and end as a product. Now, shown here is an exothermic reaction in which energy is released. We know this because products are at a lower energy than reactants. However, notice every one of these reactions requires something called activation energy. In order to get started, we have to put energy in order to get to our destination, which is our products. Now, reactants, in order for reactants to react, they have to come together and collide. Now, this collision is going to be a much higher energy change. So here we call this the transition state, and for some reason we denote it with an unequal sign. Now, this unequal sign tells you that this is the most uncomfortable a reaction will get through its transformation. Now, notice we have here an endothermic reaction where delta H is positive. We know this because the products are at a higher energy than the reactants. Notice, however, the activation energy for this reaction and this reaction are the same. They require the same input, but they're going to get a different energy output. Now realize, in order for a reaction to have enough specific activation energy, it has to rise to a certain temperature. The entire system needs to be at a certain temperature for it to work. Now, we can actually run reactions at lower temperatures if we change the energy of activation. Now, how we do this is with a catalyst. A catalyst lowers the energy of activation. Notice that we can decrease the energy of activation by adding something else. Now, something important to understand about a catalyst, catalysts go in and catalysts go out, and they do not change during the course of the reaction. The only thing that a catalyst does is it facilitates reactants to turn into products. We discussed in class that this is the difference between cutting bread with a knife and cutting bread with a finger, for example. A knife enables you to cut bread in a much more concise manner than something like a finger. And the reason why is because that tool is more used to getting you through the transition state, which is the separation of the two pieces of bread. A finger isn't sharp enough to actually go through it, so you're going to end up ripping it and getting it to a much higher energy than it initially would. Now, we also have these Boltzmann distribution curves. What they are is based on speed. So it's showing the population of molecules at specific speeds. Now notice it's a standard distribution, similar to any sort of grade. Now notice here, this is the place where majority or the average amount of molecules exist. They exist at this speed. Now notice that everybody has a different speed on this probabilistic curve. And what we can see is if we increase temperature, this population will shift along with the speed. So our average actually goes higher in speed, but more importantly, we have the same distribution, meaning we can't change the number of molecules. So what must happen is the number of molecules at the mean has to go down. So now you have the same exact amount of molecules underneath the curve. However, you have a different distribution. And this is all done by increasing temperature. Now, if you do the exact same thing with this Boltzmann distribution curve, but you decrease temperature, how's it going to look? It's going to shift the same population to the left, but that mean is going to go up because now you're condensing the same amount of molecules in a much smaller distribution. So the higher the speed is, the greater the difference in distribution is. The lower the speed is of the average, the lower the distribution. So therefore it must be higher. Now, important to understand, where does energy of activation come into all of this? Energy of activation is at a specific temperature. So therefore, there's always a specific speed that goes along with it. So let's say in this example, we're taking a reaction and increasing its temperature. Most of the molecules here have not hit the energy of activation, but once we increase it to a specific temperature, majority of that population have gotten to that activation energy and will start the reaction to finish and go to completion. Now, in this specific case, if we have the exact same example, by lowering the temperature, we do not have an ability to have the population go over the activation energy and react to completion. So in order to have a reaction work and go through its activation energy, go to the energy of activation, you need to increase temperature, and this is typical. However, in a catalyzed reaction, what you're doing is you're actually decreasing the energy of activation. So therefore, you're able to get a population of molecules to reach the energy of activation at a lower speed. The next topic on our agenda is reaction mechanisms. As we've seen in potential energy diagrams, reactions undergo what we call steps by going from reactants to products and running through activation energy. Now, some mechanisms undergo multiple steps where you have multiple activation energies. Now, when this is the case, one step within the entire reaction will be what we call the rate determining step. The rate determining step is the slowest step in the reaction that governs the rate law of the reaction. Now, in this example, I show a bunch of funnels where a small funnel ends up getting backed up by water when trying to pour water into this flask. Now, depending on the position of the funnel, depends on where the backup actually is. Now, what we've learned through reaction mechanisms is the step with the highest energy of activation runs the slowest. Therefore, the step with the highest energy of activation is the slowest reaction. So when you're given a set of steps and you find a slow step, that is the rate determining step, the one with the highest energy of activation. So let's see where elementary steps fit into a net equation. So we usually see net equations for reactions, but through kinetic studies, many people try to figure out how a reaction runs from A to B. Now, we know that we're starting here at our reactants and we end up at our products. I'm just going to assume that this reaction is exothermic. And what the kinetic study is professing is that it ran through 3 steps, where the first step was the slowest step, which we believe is the RDS. We know it's the RDS because it says slow. We know it's bimolecular because it involves 2 different molecules hitting into each other. So this most likely will get us to a much higher intermediate level. Now, generally speaking, elementary steps are endothermic, and the last step is usually exothermic. When it's fast, it usually means that the energy of activation is tiny, and that usually results in an exothermic reaction. This isn't always the case, however. So now that HOOBr has been created from the initial step, now this will undergo a secondary transformation where it becomes 2HOBr. Now this will have an energy of activation, but notice it's got to be lower than the activation energy that's required to get you to HOOBr. Now, after this is the case, we have to undergo a third and final step, which is one of the HOBr molecules is going to interact with hydrobromic acid and become water and bromine. And this will get you to your end product. So notice you now have 3 elementary reactions with 3 different steps and 3 different activation energies. 2 that are fast, which are small, energy of activation, and 1 that's large, which is the rate determining step. Now, this is going to take the longest amount of time getting to this intermediate here. Now these, because the energy is already high, will easily go through and convert into water and bromine. Now, one last word about elementary steps. We have to look for something called intermediates and catalysts. So we know about catalysts. If we have something going in that ends up being untouched and going out, that would definitely be something to look for a catalyst. Now this one doesn't have any of these examples, but the way to tell is by canceling materials out. And if you have a product and a reactant and a product that are identical, that must be a catalyst. But this one does have intermediates. Intermediates are the things that are created and then destroyed throughout the reaction steps. Now, how you find intermediates is quite simple. Look at a net equation, and if you're not involved in the net equation, then you must be an intermediate or a catalyst. Now, if you're being destroyed, you must be an intermediate. So, for example, this peroxybromine or peroxybromide is an intermediate because it is created in this step, but then it is destroyed in this step. So again, catalysts don't get created or destroyed. This one gets created and then immediately destroyed. So we know that this is an intermediate. Okay, let's see if we could spot any other intermediates inside of here. Well, HOBr is also an intermediate because one of them is created. Now realize that this also exists in the product, but one of them is created and then further destroyed. Now, one of them is not an intermediate and the other one must have been.